Benedikt Halldórsson, that now is promoted to a research professor in earthquake engineering at the Research Center, University of Iceland. He has a versatile background in geophysics, civil engineering, and engineering seismology and earthquake engineering. On a personal note, I tease sometimes the faculty at the engineering department that there is not enough collaboration with the earth science faculties. And now appears a person who has a very, very diverse and versatile background, and in fact is a hybrid of the two. And where else in the world is it more appropriate than in Iceland? Benedikt graduated in geophysics from the University of Iceland in '94 and has a master degree in civil and structural engineering from the University of Iceland from '97. He did his PhD in structural and earthquake engineering at the University of Buffalo at the State University of New York in 2004. In addition to his versatile background and more on his hybridization, he was a field assistant after geo in the summer of '91 with renowned geophysicist Bruce Julian and Gillian Folger, where they were doing seismological research in Hengill in Iceland. And usually work like that sets its marks on students. And later on in a research project, he was associated with Professor Julius Solnes at the Faculty of Engineering at the University of Iceland in '94, and with Professor Ragnar Sigurbjörnsson, the head of the Engineering Research Institute at the University of Iceland. And here comes the hybridization, Páll Einarsson, a professor of geophysics at the Science Institute of the University of Iceland. So the promotion and the hybridization of the two fields is not a new thing, but now is coming to fruition with the promotion of Benedikt. He was a lecturer at the Department of Civil Engineering from '97 to '99, research assistant from '99 to 2004 at the University of Buffalo. He was a postdoctoral fellow at the Multidisciplinary Center for Earthquake Engineering Research in Buffalo from 2004 to 2005, and from 2014 to present, a research professor at the Earthquake Engineering Research Center, University of Iceland. He has received several awards as a student and professional, and the most prestigious of which is an international award in the field of earthquake engineering and seismology, and that is the ECEES Award for Excellent Contribution by a Young Scientist in 2006 on the first European Conference on Earthquake Engineering and Seismology. He's been an extremely active and productive leader in many international projects on the research, teaching and infrastructure development. And among the research grants he has, in 2014, he has a Grant of Excellence from Icelandic Center of Research, and where his role is a principal investigator, and the project name is Real-Time Earthquake Fault Monitoring and Seismic Risk Assessment using dense geodetic and seismic arrays in urban areas. And what is interesting about this is that this is the first engineering promotion that we have, and which is different from the usual scientific promotion from the Scientific Science Institute, since the engineering faculties and the engineering research do not have the same basis as the others. So Benedikt's achievements are extraordinary in the sense that the backup and the infrastructure for the research is not comparable to what we have in the other science fields. And with this, I think our goal forward is to build infrastructure in the field, in the selected fields, and build on the good work that the colleagues and people around have generated. So in his grants and awards that he has received, they include equipment. He has received research, teaching grants, and he is also has some impressive publication records that he has published 12 papers in the ISI journals. And in the light of the in the light of the spare infrastructure that he's building on, his achievements are significant. Also, in addition to all this, he's also been involved in supervision of graduate students, in research students, and helped build the tradition of engineering education, taking that to a level higher than before. He is currently supervising 4 doctoral students, 4 master students, and has received and is currently running 3 interns. The main interest of Benedikt, he will go through them himself, are in basic research and engineering, industrial research and development, infrastructure development, but in addition to that, he also has interest in teaching and supervision of students. With this said, Benedikt, I invite you to go ahead and do your lecture, and at the end we will have some questions, but we will celebrate with you going forward, and the floor is yours.
Thank you very much for kind words. Welcome everyone. Good afternoon, and thank you for coming. I would like to approach the presentation of an overview of some of my research by looking at the main focus areas that I've been working on over the past few years. I will be talking about the first 3, which include the basic research in engineering seismology and earthquake engineering, and also infrastructure development of measurement systems and installation here in Iceland, and also I will mention industry research and development, in particular the development of new techniques in strong motion monitoring. But engineering education is also close to my heart, and I've been, in addition to supervision of masters and doctoral students, I've been involved in the feasibility study of developing graduate programs, and in addition to that, establishment of exchange student agreements between the University of Iceland and international institutes and universities. But I will start by approaching the topic of earthquake engineering and engineering seismology research by presenting you with a map of Iceland showing the locations of the main earthquakes that we have records of. And please do not be discouraged if my slides have a lot of information on them. I will avoid the details. I will talk about the general issues and let the figures do the talking for me. But here I would just like to point out that the gray areas denote the earthquake and volcanic zones of Iceland. But interestingly enough, the strongest earthquakes that we have experienced here in Iceland, they take place in the areas between those zones. Here in the South Iceland seismic zone, and in the north of Iceland and off the coast of Iceland in the Tjörnes fracture zone. Now, these areas here, especially here in the south, is where the strong earthquakes combine with considerable population density and infrastructure. And that has effects on the earthquake engineering aspect of our research. We deploy our instruments in the areas where we have both strong earthquake occurrence and where we have population and infrastructure. Therefore, you will see that our stations are in buildings. They're in power plants and in dams, and also in office buildings as such. Now, I have, from 2006, I've been involved in the development, design and installation of a new breed of strong motion instruments that have been deployed in a different setting than these instruments that you see here. And those we call strong motion arrays in urban areas. And I've installed two, one in Hveragerði in South Iceland and another one in Húsavík, and I will mention them later. Now, if we look at the South Iceland seismic zone a little bit closer, we have here the distribution of stations. And in general, there are about 10, order of 10 kilometers between the stations, which is a traditional setup of, I guess, a setup of a strong motion network. And this network has been, was developed and installed, or the deployment of it commenced about 30 years ago, and has been the backbone of the research at the Earthquake Engineering Research Center since then. In 2006, when I came to the Earthquake Engineering Research Center, this essentially was the picture in South Iceland. The most significant earthquakes that took place in South Iceland were the magnitude 7 approximately in 1912 in the eastern part of the South Iceland seismic zone, and then the two earthquakes in June of 2000. And in the development and site selection of this new network of dense instrument arrays, I was looking at this area. And the most suitable site selection we deemed was Hveragerði, and that's where the array was installed. So in terms of infrastructure development, strong motion arrays in urban areas are a particular research tool that I have been working on since I came here. This map shows a map of the street layout of Hveragerði, and the blue dots and the triangle are the instruments locations. Now this is as it was designed. There are a little bit fewer stations today, but the array was designed for multiple purposes, from monitoring earthquakes, for enabling estimates of ground motion characteristics that we did not have reliable estimates of before, to provide geophysical information, insight into earthquake source processes, and to take advantage of the powerful methods of array processing techniques. And this layout was designed to optimize for all these purposes. Now, in 2007, where most of the work was done, one thing was clear from the outset, that installing instruments in a configuration like this, even in a small area, did not yield the expected results right away. And that's when, upon looking at the data, there was a problem in the fact that not all instruments were recording earthquakes. So the solution that we invented and worked on in collaboration with our New Zealander instrument developer was a control server that actually converts networks to arrays. Essentially, a network of instruments can form an array if the instruments have a common time base, if the same clock is ticking in all of them. That opens up a whole wide array of new possibilities. Now, the way it works is that we had to have all the instruments internet connected all the time. And the flow is, and I won't go into detail here, but if we look at these triangles here as the stations of an array, and an earthquake happens, and only 3 stations actually record the earthquake, That is, they actually wake up and record the earthquake, and the other stations, they don't. These are instruments that are located in a town where there's noise, there's different sites have different sensitivities, and but the power of the array processing and the quality of the data that we can collect is dependent on how many stations actually record the earthquake. So the system revolves around receiving signals from those stations that wake up. And the control server decides, is this an earthquake? With a very simple algorithm, it can determine that with a very, very high degree of accuracy. If the answer is yes, it is an earthquake, it sends out a signal to all the other stations and wakes them up. And they start recording the earthquake. That way, we ensure that we have a complete record of the earthquake on all instruments. Moreover, these earthquakes that are associated with such signals are significant earthquakes and are high quality data, and we can simply discard anything else. And this leads to a drastic reduction in the time that is needed on behalf of an analyst to look at data and determine if this is something worth looking at or not. So we can actually just let the control server collect these data, and then after a while we can look at it, and with close to 100% degree of accuracy, these are actual earthquakes that we are left with. So local disturbances, if someone drops a load of their truck next to the house and a station wakes up, that we don't save that at all. It has led to, it's been a real time saver, and we've published on this. But this came in handy a few months after we installed it, when an earthquake took place in South Iceland. And I'll bring you back to this area here. We look at this red rectangle here. Hveragerði is here, Selfoss is here. So this map, Hveragerði is here, enlarged over here, and Selfoss over there. Ölfus over here. This was the situation on 29th of May in 2008, just before 3:46 in the afternoon. Then a few hours later, so many earthquakes had taken place, the main shock and the aftershocks, that when their locations are plotted on the map, it looks like this. And our data tells us that the hypocenter, or the epicenter, where the rupture started, was located approximately over there. The aftershock distribution is always an indicator of the extent of the earthquake rupture. This was the initial estimate, and we know from the tectonics of South Iceland that the movement is right lateral. If you stand on one side of the fault and you look at a person on the other side of the fault, that person looks like it's moving to the right during the earthquake. And then approximately 2 seconds later, the second fault ruptured, and right next to Hveragerði. And here is a nicer figure of the situation. And this earthquake was, and is to date, the most expensive natural disaster in Iceland. And it caused widespread damage, but fortunately no lives were lost. It was quite clearly a complex event on two parallel faults. But the ice array network in Hveragerði produced a worldwide unique data set of strong motions in the fact that it was a magnitude 6.3 on 11 stations at the distance of approximately 1 kilometer away from the fault, one of the causative faults. And the data looks like this. This is the recorded acceleration. We record acceleration because it scales proportionally to the earthquake action on structures. And acceleration is a change in velocity of the ground. And at all sites, we see the same pattern, high frequency motions. This is about 15 seconds shown. And we also see some low frequency components. In general, these are similar recordings, but they have significant differences. And this is the east-west acceleration. The north-south acceleration, since we record on 3 components, looks like this. Same characteristics, rich in high frequency, but with low frequency component embedded. And the higher frequencies are more active in the vertical motions, that is the vertical shaking of the ground. But picking out the maximum acceleration values from all of the stations for the horizontal components, which would be then the collection of peak ground accelerations, we plot them up as a function of distance away from the epicenter, and it is clear that this is the IsoRay data, and the other data are from the rest of the strong motion network, and it's clear that this data defines the near fault ground motions in terms of acceleration quite well, and is a rather dense data set. It is natural that the ground motions, they become lower the further you are away from the earthquake, and which means in turn that the closer you are to the earthquake, the more effects it has on you and structures. And we estimate the effects on structures by using the recordings to calculate the pseudospectral acceleration response of structures, simple structures. And for the collection of data in Hveragerði, the gray area for the north-south component shows the variability of these motions. And the black line shows the current earthquake design requirements for the area. But for the vast majority of the structures that were built a few decades ago, these requirements were half of what this black line is. So it is clear that the earthquake loading on structures was much higher than they were designed for, and therefore more damage could have been expected. But fortunately, there was actually less damage than the ground motions were indicating, primarily because of the ground motion had a very short duration. It took a very short time. And the low-rise building styles that are predominant here in Iceland have considerable reserve strength. But another feature in the data are long-period energy that show up like so in the pseudospectral acceleration in both components, north-south and east-west, that the design requirements do not take into account. So it is an important observation because this type of action is something that we can always expect here in South Iceland due to the regularity of the strong earthquake occurrence, the type of strong earthquake occurrence here in South Iceland. Now, the blue dashed line shows the mean value, so the gray area indicates there is a variability in these effects between stations. And this is estimated using the coherency function, or calculating the lagged coherency matrix, which essentially tells us how similar are the ground motions of two stations that are separated by some distance. Let's say there's a 1 kilometer between the stations. Then at low frequencies, the ground motions are very similar, but as soon as we reach the higher frequencies, the similarity disappears. And but such results are especially useful for estimating the seismic loading on extended structures, and which have many times been termed the lifeline systems. We have also estimated from the acceleration, we have estimated the velocity, and the velocity in east-west is shows at all stations the so-called near-fault pulses, which are these regular pulses in the data. We also see this in the north-south direction, but it is of a different, it looks different. It is, has two peaks, both towards north. Now, when we calculate the displacements along the east-west directions and the north-south direction from these from the data, then we can plot on a map the movement of Hveragerði during the earthquake. This map here shows north and south, east and west, and these are centimeters. This is the location of Hveragerði before the earthquake took place. This is the location of Hveragerði after the earthquake, about 20 centimeters to the northwest. And it took a very short time. So the town, the length of this path is approximately 1 meter, and first it starts by moving slowly to the west, then kicks north, and then is flung back and forth until it stops about 20 centimeters northwest of the location where it used to be before the earthquake. This particular movement is rather striking, and it took place over here, but Selfoss is over here, so almost on the opposite side. But the movement there is in the opposite direction, as we would expect, to the north, to the southeast, but has a less striking character. And this indicates complexities in the earthquake source. And how do we quantify these? One obvious way is to simply state that, well, the basic complexity is that the earthquake took place on two separate faults. North is over here, east is over here, Selfoss is located here, Hveragerði over here. And this is a three-dimensional image of what GPS studies indicate is the extent of rupture on the fault plane, and also where the rupture took place. Red colors indicate 2 meters of slip at depth. Now, the GPS measurements give us the static motion. We don't know when this slip happened, but by the engineering approach, we assume a simple distribution of the earthquake slip, starting here and then spreading circularly in all directions until it jumps to the second fault about 2 seconds later and then ruptures that fault. The results, when comparing the ground motions, the low frequency ground displacements at Hveragerði and Selfoss, are pleasing. The east-west component of displacement of data is the gray line, and the black line is the result of the simulations. The dynamic part of the ground motion is captured quite well, but the static offset less so, and there are certain reasons for that. But in general, it captures the salient features of the displacement time history. Capturing them in more detail requires more information on the earthquake source, information that we may not have. But these are numerical results. And we can also start by looking at the earthquake source itself. Do we describe it with a simple model, or do we use a complex model? A simple model is describing the entire earthquake as a single circular fault that ruptures. A complex model is to look at the fault plane being composed of sub-earthquakes. And the model that I've been focusing on and developing is the specific barrier model, which I believe is the perfect hybrid between a simple physical models in terms of application, but capturing the complex nature of earthquakes, earthquake sources at the same time. Now, it involves taking simple earthquake source models and representing them by a complex one that still requires relatively few parameters. And we want to see if we can retrieve those parameters from earthquake data that can be useful in the simulation of future earthquakes. And at the same time, give us geophysical information on the parameters that control the model. But the model works as so. We imagine a three-dimensional fault plane at depth, and we postulate a hypocenter on the fault plane, and then the rupture spreads, and each time it spreads, each sub-earthquake, so to speak, ruptures and sends seismic waves to the station. And this is particularly useful for near-fault simulations, because the seismic signals from each sub-earthquake are different depending on where they are located and when they ruptured relative to the hypocenter. But summing up all these simulations results in the final time history of acceleration, ground motion, that we expect here. And using a phenomenological model for near-fault pulses, we generate realistic-looking time histories that can be used for design. And we have carried this out for a number of earthquakes with good results. Here's an example of the Northridge earthquake that here shows a vertical projection of the fault plane modeled as the specific barrier model. The simulated acceleration time history versus the data. Another station for the Northridge earthquake, simulated time history of acceleration versus data. There are some good examples that I'm showing here. We also simulated the ground motions for the Chi-Chi earthquake, which was a much larger event. The black line here shows the surface rupture. The hypocenter was located here. And then we've also done basic simulations for two of the South Iceland earthquakes, where this is the synthetic acceleration with the near-fault velocity pulse that we, in this case, copied from the data to exemplify the simulation method. But these are, again, numerical results. I've also looked at this in theoretical sense, in quantifying, in addressing one of the criticisms that may be addressed to the model, is that this specific barrier model with the regular size sub-earthquakes is relatively simple. So I've investigated theoretically what it means to relax this constraint and allow for a distribution of multiple size sub-earthquakes. I've also looked at the indication, if we look on a map, if this black line is an earthquake fault, if the rupture starts here and the ruptures in this direction. If you're sitting here, you are receiving the rupture, and if you're sitting here, you are behind the rupture in a sense. I've also looked at what that means in terms of the radiation from the seismic source, and allowed for variability in those estimates. And the mean value, the simplest case of the specific barrier model, is shown with the blue line. This is the earthquake source spectra for a magnitude 7.5 earthquake, and this is for a 5.5. This is what one would expect when receiving the rupture towards you, and these results you would get if you are behind the rupture, so to speak. But this shows that the simple model is always the most applicable at any given time to begin with, unless we have additional information or the data warrants a different approach, more complexity. But I would like to, the last part is I want to present to you the project that received the Grant of Excellence this year. And it involves Húsavík in North Iceland. This is an overview map. Húsavík is located here, and it is sitting on the largest transform fault in Iceland that extends on land to the northwest, out into the Skjálfandi Bay, past and underneath Flatey, and into the Gulf of Eyjafjörður. And current estimates say that at the moment it is due for a magnitude 6.8 earthquake, which is an estimate, but the last earthquake on this fault took place 140 years ago. Now, looking closer at this area, the project revolves around a combination of two infrastructures, of the latest technology of GPS measurement systems that are capable of sampling at around 50 hertz, and the latest technology of accelerograph systems, strong motion instruments, which are denoted by the red triangles. And the combination of the two at 3 sites inside the Húsavík town. And that way, this array, ICE Array 2 is phrased, traverses the Húsavík Flatey fault and monitors both slow tectonic movements and also fast tectonic movements. Slow meaning the spreading, the tectonic spreading, and fast meaning earthquakes. If we look closer at Húsavík, it is clear that the color scheme shows the elevation differences. The valley that Húsavík sits in is actually a rift valley due to a bend in the Húsavík Flatey fault, and the old part of town is at the bottom of the valley, but the newer parts sit in the hills above. But these hills, and I should note that these red lines are the surface traces of this fault, believed to be about, like I said, 100 kilometers long and about 6 to 9 kilometers deep. So it is sitting right on the fault, this town, and has different elevation differences inside the town. And moreover, the geological units of the hills to the south and to the north are of completely different material. And still it's different than what we have in the southern part of town. So it's from engineering, earthquake engineering experience, the elevation differences and geological differences, they have quite effects on the level of ground motions expected. These levels of ground motions, they are transmitted into the building stock of Húsavík. Now the buildings have different sensitivities to earthquake ground motions. The old buildings, they are much more sensitive to to earthquake ground motions. They are shown in the red areas here. But the vast majority of the buildings in Húsavík are shown in the dark yellow color here. But the green shows the newest developments, which are fairly robust in terms of earthquake safety. But during a recent earthquake sequence, we recorded the largest strong motion data set that has ever been recorded for North Iceland. But the earthquakes took place far away, and they were relatively small. 2 of them were above 5. And for Húsavík, the earthquake action on structures was not even close to the design criteria as it was for the majority of structures in Húsavík. But what is interesting is that depending on where we are looking inside the town, different earthquakes show systematic dependence on the relative levels of ground motions inside Húsavík. So at site C, we always see larger ground motion than in site B, or site A. And this is true for all of the earthquakes we recorded and we are currently analyzing. So this systematic dependence is what we want to quantify. And quantifying it means also we need to take a look at what is underneath the buildings and see if we can quantify that as well, which are called the side effects and have considerable influence on the ground motions. So in summary, the ISARRAY 2 project is underway, and currently 3 doctoral students have already started. Tim Sonneman, Sahar Rapema, and Milad Kozari. We are looking at the strong motion data, both in Húsavík and in Hveragerði, because Hveragerði, the ISARRAY in Hveragerði, recorded in 1 year after the Ölfus earthquake 1,700 earthquakes, 1,000 of which were not reported by the IMO. And we believe that is a considerable data set that can perhaps constrain some of the estimates that we are looking for. But we emphasize physical modeling in this project and have not yet started analyzing GPS data and acceleration data together. We have a structural monitoring system for the Húsavík Hospital that we hope to install this winter. And the expected outcomes of this project will hopefully be meaningful for a variety of professionals, engineers, geophysicists, geologists, urban planners, and the municipality. But ultimately, the purpose of such engineering seismological research, as I've been describing, is to produce results that not only are useful in terms of basic research, but also useful for that can be used directly, both by minimizing the effects of earthquakes in the community, useful for engineers, and at the same time serving the purpose of increasing our knowledge and understanding of earthquakes and their ground motions. And this is ultimately the goal of engineering seismology, which is my chosen field. With that, I thank you very much for your attention and thank everyone involved. You know who you are. Thank you.
And now for the last time in your professional life, you're going to be treated like a student and put on the barbecue for questioning and discussions. And I get the privilege to start, I know you built on experts and professionals. That some are here with us that have devoted their whole professional life to this, and you're really carrying on from those. But looking forward, what kind of measurement techniques are you predicting, or do you foresee as the next step? And what is the next measurement techniques that you expect to see? Because this is a new way of capturing data through the structures and different site selections. But what is the next level, you think, in measurement techniques?
Well, in general, I believe that you cannot rely on a single measurement technology to tell you everything. You need to know about the natural phenomena like earthquakes. So multidisciplinary approach is definitely desired. Combining the latest technology, GPS measurement systems, and the accelerographs is as in this project is an exciting project, because theoretically, if we are able to calculate acceleration from the GPS instruments and displacements from the acceleration instruments, we have essentially doubled the network size of both involved. But the next steps, what I would particularly like to see is something called 6 degree of freedom accelerographs. That we have the project outline ready for with the instrument manufacturers in New Zealand, and this in order to capture the entire motion using a single instrument, the 6 degree of freedom instrument is needed. Also, this would be new because I am not aware that these instruments exist, but we have a plan to make one if we get the funding, and it can serve multiple purposes. You can use it at the top of buildings to capture the complete motion of a building that is subject to wind load or earthquake load, and to deploy such instruments in the near fault region, close to the earthquake faults, would be very exciting to measure one of the first estimates of rotational ground motion, which right now we only estimate. So these are the exciting things in my opinion.
This was a loaded question because what I really like to see is how you blend in and how you change the traditional, maybe geophysical approach. You apply engineering to it and you take it into practical applied science immediately. And the loading of this question was what other faculties and what other expertise can be called upon.
Well,
because you mentioned the equipment comes from New Zealand.
Yeah, and those are electrical engineers.
Exactly.
Yeah, and they definitely needed our input in developing the instruments that we purchased from them for the array, which have gone through several cycles of operating system upgrades and hardware upgrades. But we also need the seismological theory to predict what we should be seeing from the instruments, and so it spans geophysics, engineering, electrical engineering, and computational science as well. Material science, definitely. Optics. These are all specialists that would be very useful to such a project.
I was impressed. I remember seeing an FEM from Sigurður Brynjólfsson on collaboration between in a material science approach with geophysicists. 15 years ago or something. I don't know. But open the floor for questions if there are more questions. Sigurður.
Thank you very much, Benedikt. Very impressive lecture and very impressive work that you have done, and you showed us very clearly how basic research can be connected to applications, and I'm convinced that your work and your teams and the people that maybe came before you saved a lot of lives in 2008. So I think it's very practical stuff. You mentioned Húsavík as well, and your newest project is there. And you mentioned that the last big episode there was 140 years ago, if I remember correctly. Could you tell us a little bit about the history before that, and maybe what you expect, let's say, in the next few years or decades? I know you don't want to predict, but can you tell us about the history?
Well, I'll. So that I won't get anything obviously wrong, I'll talk in general sense about the history there. Essentially, the tectonic displacement that takes place in North Iceland is split between the Húsavík-Flatey fault and the Grímsey ligament. The Grímsey ligament takes about 60-70% of the motion, so a smaller part is taking place on the Húsavík-Flatey fault. So it means that it takes longer time to load up for the next strong earthquake. But there's a considerable difference between those two ligaments. There's volcanic activity associated on the Grímsey ligament, which possibly segments the earthquakes that take place there, while the Húsavík-Flatey fault appears to be much less segmented strike slip fault. So potentially larger earthquakes could take place there, potentially. But the most recent research, both historical accounts that have recently been dug up, have introduced a considerable number of events to the catalog, which was much less reliable than the one in South Iceland. And the latest trenching, meaning digging into the fault itself, and geological research seems to indicate that the Húsavík flæðifault was much more active than previously thought in the previous thousands of years. So this may potentially affect the estimate of the seismic hazard that we rely on in design. And so while not predicting anything, I think the most recent research, both geological, historical, and also measurements that we've made there is definitely supports our choice of this place being ready for some large-scale research. So, and this project, which I forgot to mention, is in collaboration with Dr. or Professor Sigurjón Jónsson at KAUST in Saudi Arabia. There are multiple factions in the scientific community that are interested in this, that are converging on this place. And so it was a natural thing to combine our forces and create a strong project.
I'm just wondering, thank you very much for your very nice presentation. It's a very impressive research you've been doing. So sitting here and thinking about all the measurements you've been doing, are we getting closer to be able to predict like large earthquakes like in 2000 in South Iceland?
I'm not sure I know how to answer that, and I definitely want to avoid answering that, because the earthquake occurrence in time and space is not the focus of the engineering community. The focus is on quantifying the ground motions that earthquakes of certain properties are able to produce, and we want to look at those values and see if that has any effects on how we approach building design. Because if forecasting the earthquakes, if all the buildings are essentially safe, then forecasting the earthquake is maybe less of a critical issue in terms of saving lives and infrastructure. So, but the earthquake engineers decades ago decided that you needed three things to predict earthquakes. You have to know how large, where, and when. But you need to be able to talk about all three things simultaneously and with reasonable accuracy. And if you don't have any one of those, then you should just keep quiet.
Hjalti.
Thank you, Benedikt, for a very interesting talk. I was interested, I guess I had a similar question to about all your measurements are measuring things that are as they're happening. But is there no way of measuring, some kind of stress or tension or something that obviously is happening underground? You're just measuring it when it happens.
Well, yes. The answer is yes, and to both. So the strong motion recordings record things as they are when they happen, and but long-term research projects using, I would guess, multiple systems, sensor systems, GPS, for example, I think are crucial in this respect. To essentially, this is a mechanical system. If we look at the crust as a solid body with some properties, and then different sides are moving in different directions, and that is essentially an exercise in continuum mechanics, how you estimate the stress buildup. But then, what is the fracture criteria that you need, and is the involvement of heterogeneities in the Earth, different levels of sensitivity to load that we may not have any idea of. But in my mind, multiple multidisciplinary measurement systems, I think, are required from geochemistry to geodesy and seismology as well. Shallow seismology, deep seismology, all these are, I think, need to be combined. And but that's I'm almost a layman in those terms, so I'm essentially just telling what my feeling is.
Thank you, Benedikt. You showed some interesting graphs of displacement of Hveragerði. Was there any vertical displacement?
Yes, there was.
How much?
But it was about 4-5 centimeters elevation, if I remember correctly.
So did it
Yeah.
end 4 centimeters higher or lower? Or
Well, it had a permanent offset, if I remember, about a few centimeters in a vertical direction. But this was the case right after the earthquake. Now, in the years since then, there is post-seismic relaxation. So I'm not sure what the situation is now, if things have been moving back or to some extent.
Thank you for a very good and interesting talk.
Thank you.
You showed a measured spectrum of a response curve and compared it with a design
Yeah.
response curve, and how your measured response exceeded those of the design.
Yeah.
And furthermore, would have different character, also with a longer frequencies. Have those design displacement response curves been updated to reflect your measurements? And I guess it's a twofold question. And then you also showed your modeling, how that could actually quite well capture the surface displacements. If another event would occur in this area, could this model been used to assess if the design curve should be exactly as your measure spectrum are as present, or if they should be updated even to a different character?
Yes, I definitely think so. We have more measurements from past earthquakes in June 2000, for example, in addition to this last earthquake, 2008. And I've not been working on the design spectra or the modifications themselves, but at the center we've done considerable work in quantifying the characteristics of the near-fault motions, with particular focus on what that could mean in terms of earthquake design. And yeah, I guess that's essentially it. And using a particular model, like I was showing, it can definitely be used, but the model that I'm using is I won't say more complicated and needs more input parameters than is desirable. So, but based on the data that we have here and in other places, we're actually able to combine these data and obtain the main characteristics of near-fault motions to make decisions on or to essentially present the design curves that could be appropriate. But the models that I particularly showed have more to do with investigating if earthquakes and Iceland, South Iceland is a perfect natural laboratory for this, is to see if these earthquakes have very similar characteristics, and assessing in terms of their source properties, where we start with. If we can pin down these parameters to certain values that have some uncertainty, and have relatively few values that we can base modeling on, modeling time histories of ground motion. But the spectra that the response spectra that one expects in the near fault region, considerable work has been done at our center in that regard.
They say, the geophysicists say that in the south of Iceland you can find 1,500 experts on earthquakes. And you may say that the team in Selfoss has actually brought seismology to their homes in terms of measurements. But there's no coincidence that it is based in Selfoss. I know the team in Selfoss is very proud of you, and to congratulate you, and thank you for your lecture. You're now
Thank you very much.
Now a research professor at the Institute, and we hope to see more students and more work coming out of you, and so that the continuum to what you based on may flourish in the future. Congratulations.
Thank you very much.
And following, we will have some drink in the bar.